Good morning, everyone. My name is Chen from Institute of Information Engineering, Chinese Academy of Sciences, and this is a joint work with Indiana University Bloomington. Our work is mass discovery of Android traffic imprint through instantiated partial execution. At first, let's answer three questions to introduce why we work on this project. The first one is, why do we extract traffic imprint? According to a chart which comes from 2017 Cisco Global Mobile, this gives information on global mobile data traffic from 2016 to 2021. In 2016, the mobile data traffic is amounted to 7 exabytes per month. And in 2021, it is expected to reach 49 exabytes every month. So mobile data traffic becomes a huge share in network traffic currently and future. Considering the security, this mobile data traffic increase gives great pressure on today's network security infrastructure. Like the desktop software and web applications, mobile data are also supposed to be under the monitoring and protection of network security infrastructure, such as enterprise, ISP, and carriers. There are two types of mobile apps are asking for the monitoring. First, PHS. With the threat of the potential harmful unrest, there is a strong demand to detect them on the network level, such as use anti-malware system deployed by the individual organizations or mobile carriers. And second is the legitimate apps. Those on the BYODs are increasingly required to be controlled by the next generation firewalls to manage their access to resources. So to serve this purpose, the first step and the most important here is the identification of individual apps from network traffic. And this is why do we extract a traffic imprint. We are going to use a traffic imprint to identify the individual apps from network traffic. So this is by no means trivial. However, the second question is comparing to the metro desktop software identification. What differences are between mobile and desktop and application identification? Usually, we use protocol port number to identify the desktop software. But different from desktop software, mobile applications mostly use a HTTP protocol, and their port number continuously changing in every HTTP packet. And we also considering other methods to extract the imprint. For example, but there doesn't work. The first one, every packet doesn't contain the app names in the user agent of the HTTP header as recommended. And second, looking for the servers the app talk to doesn't work either, simply because increasingly the same host names also often belongs to a shared library. So they service many different apps at the same time. So considering these differences, we can use a technique of identifying desktop software on mobile application. We need a new technique to extract imprint from mobile network data traffic. So the second question is, what challenges are we facing while extract imprint from the mobile network traffic? It is obvious that we can use a manual analysis, although some next generation firewalls still do it manually today. But it is impossible to handle multi-app minions from various markets, and it is even very difficult to handle hundreds of apps reported by VirusTotal every day. And there are some attempts to automate this process. For example, they analyze app traffic, such as from ISP. But here is a question: how to systematically generate app network traffic before the imprint can be extracted? And some companies run the app in a virtual environment and try their best to trigger as many network activities as they can. Even if they use a more targeted UI exploration tool, it is still not suitable for a large scale because there are some fundamental limitations. The first one, no one knows how long an app should run to get all the network traffic. The second question, the app contains special triggers such as user login and more deep human involvement. And more challenges is on the PHA. A PHA may contain a carefully crafted conditions such as time, location, event, and etc. So designing a new technique to discover imprint more comprehensive and scalable, high scalable is the aim of this research. Let me give you a brief high-level idea of our Tiger. Our system is called Tiger, Traffic Imprint Generator. Because since the dynamic tool is hard to trigger all the network activities, so our approach is going to static find all the packet sending APIs as the network things. And then we backtrace from every network things, and we execute each slice to get an output value. The output value is exactly the content of packet. So finally, we find the invariable portion of the tokens to construct the imprint. During this process, it's a traditional way, but during this process, the red part is most time consuming. So we are going to figure out how to make this red part process more efficiently. Our main idea is we only execute the partial code which contribute to a final invariant portion of the network tokens. So we remove the irrelevant slices. But here is a question. After we removing irrelevant slices, how to run the left slice without the values from the irrelevant slices? Our approach is going to assign a concrete value to the output of the irrelevant slices, and the left slice use a concrete value as an input to continue running program. We call this technique is instantiated partial execution. And next, we have another question: how to remove irrelevant slice efficiently? In our research, in our approach, Tiger is going to evaluate every raw variable on the slice code, whether it affects the invariable portion of network traffic token. If not, Tiger removes the subgraph of each slice and instantiates it while running the slice. So let's see the right example. For example, Tiger is going to evaluate the node C whether affects the final invariable portion of the network traffic, and C doesn't affect any invariable portion. So Tiger removes the subgraph of the node C, and the node C is need to instantiation later while running the slice. And we have two-level approaches to prune the slice code. First is cost slicing, and second is differential analysis. First, cost slicing. Here is a key observation. Mostly always, a traffic invariable token is produced from a constant value in a program. For example, the app name always comes from the Android manifest file, and a host name may be hard-coded as a constant in the program code or stored in resources files. So we consider the constant manifest file and the resources file as a sources of invariance. We expect that all the traffic tokens have a data flow relation with the source of invariance. Based on this observation, Tiger checks every variable on the slice code whether related to the source of invariance. If not, prune it. Cost slicing can be very quickly because while backtracing a method, we doesn't step into the method to do the precise control flow or data flow analysis. It's heavyweight and difficult to handle the loops and etc. Our Tiger is only scan each statement of the method and to check whether if a variable is getting a value from the source of invariance. Let's see the left or right example. For example, while Tiger evaluated the node D and the subgraph of node D, there is no there is no node related to source of invariance. The location, latitude, and longitude are variable. So Tiger removes the subgraph and instantial the D for later analysis. This is called slicing. Second, differential analysis. The idea also comes from a key observation. If an input contributes to the network sink's invariable portion, the input must also infect the invariable part of its own function's output. In other words, if an input doesn't affect the invariable portion of its own function's output, naturally, it can't contribute to network sink's invariable portion. So based on this observation, our approach uses a lightweight differential analysis to test whether an input influences the invariable portion of its own function's output. Differential analysis is doing after coarse slicing. While backtrace the return value of backtrace the function A, return value of function A, Tiger still doesn't step into the method. According to coarse slicing, we know V1 is unrelated to source of invariance. It needs to be instantial relatiinator, but V2 and V3 are related to the source of invariance. Because V1 is unrelated to source of invariance, we instantiate it. We're randomly assigning two different concrete values to V1 and set a fixed value to V3 and V2 and V3. After assigning all the input of function A, we run function A twice with these two set different values. If there is a common part between the two values, it must be come from the V2 and V3 because the V1 is two different different values. So next, Tiger is going to use a differential analysis to evaluate V2 whether affect the invariable portion of the function A's output. The high-level idea is if we change the V2's value and the common part still contain, and the return value still contains the common part, we can indicate that V2 doesn't affect the invariable portion of function A's output. From our key observation, naturally, V2 won't contribute to the final invariable portion of the network traffic token. This is a differential analysis. Using coarse slicing and differential analysis, we can efficiently remove the irrelevant slice because we don't step into the method to do the process flow analysis. We only evaluate every variable, whether they related to the source of invariance by the coarse slicing, or evaluate whether they affect the invariable portion of its function's output by differential analysis. This approach is lightweight. We can see the details in the next evaluation. In the evaluation, we evaluate text effectiveness and performances. We use around 200,000 apps from Google Play, third-party markets, and VirusTotal. For VirusTotal, we only collect the PHAs. All the experiments conducted onto Linux servers. The detailed information is on the right. The most important to under the effectiveness of Tiger is the coverage it can achieve. How many apps can be recognized from their traffic, and how many traffic can be recognized from their app identification. We randomly choose 2,500 apps from the legitimate apps and 2,500 apps from PHS to the evaluation experiment. Here is the result. The red line is a evaluation rate to answer the first question: how many apps can be recognized from their traffic? Comparing to the previous approach, which only identify an app by package name or at ID, Tiger detects 76% apps, and the increase is about 16%. The green line is an evaluation to answer the second question: how many traffic can be recognized for app identification? This ratio is very important because it's critical to decides how timely and likely an app can be identified. The more packets can be detected, and the sooner and more likely an app can be identified. In our evaluation, Tiger can detect 72% packets, while the previous approach only can detect 28%. The increase is about 44%. These increases are due to the new types of token our tigers extract. We'll talk about later. Next, performance. Here, our Tiger is for a large scale, so the key to its mission is high performance. So next, we present our effort to understand whether Tiger is indeed up to a high performance expectation. We ran Tiger against the conventional slice, full slice, and set timeouts of 10 minutes to both approaches. And full slice, and we evaluate them on 5,000 applications. The full slice spent more than 300 hours, while our Tiger only spent 5 hours go through all the applications. On the average, our Tiger only needs 18 seconds for every app. It achieves 12 speed up. And also, Tiger prunes 94 nodes on the slices code. So it is a reason why our Tiger achieves such significant improvement of performance. Next, measurement. After doing a massive study on over 200,000 real-world apps, a scale never attended on this kind of study, we are able to have an unprecedented understanding of these imprints. First, let's see the landscape. In over 200,000 apps, about 180 apps have the network sinks, and Tiger generates about 400,000 imprints among them. And except for the PHAs, other sources of apps have a high identification. For example, Google Play identification is more than 98%, and the third-party markets identification is more than 97%. The token length is also very short. They are from 9 to 338 bytes. They are lightweighted. Among all the new tokens our Tiger extracted, there are some extremely interesting. Now we are going to take a close look at them. The first one is fake device information. Device information value are supposed to change across different devices. And there is no reported that any apps can be identified by this case value, such as IME and MEI and IMSI. But in our data set, interestingly, we find that there are more than 2,000 apps have this situation. For example, the first example, an app sends out an URL containing device ID and a value. After we analyze the code, the value is actually the MD5 hash value of a string Android ID. And this traffic is sent out only while the wrap running in the background. And second example also sends a device ID and a fixed value, fixed value in the code. And the network sync is in a library. This traffic only while the host app doesn't have the permission of read phone state. These envelop tokens not only can be used to identify an app, but also reveal some interesting operation environments of Android applications. Second, hardcode time. In our dataset, more than 700 apps always send the same type to a server. Here is an example. This is a best app have a function for a chatting room. This function's traffic has a hard-coded time. It is a HTTP request for retrieving users' log chat log, always starting from a specific time. So the hard-coded time is invariable, so they can also be used in an imprint. Third, credential and personal data. Previous research reported that some apps may include hard-coded login credentials. Interestingly, we rarely saw some apps hard-coded even plain text of username and password in their traffic. Since the data is hard-coded, like the authentication and the plain text all becomes an invariable token for apps identification. And finally, to our surprise, by Tiger, we find that even some fixed session ID and cookies are in the traffic. As we know, usually session ID is generated dynamically. However, like this example, there is a fixed value in session ID. A possible explanation here may be the need for convenience, access to the server-side resources without login. And finally, let's summarize our work's contribution. We have two main contributions. The first one, we present a new technique, Tiger, using instantiated partial execution. Tiger only executes partial slices which are likely have contribution to the final invariable traffic token. And Tiger can quickly identify the traffic token for the imprint generation. Also, Tiger achieves high coverage. And comparing with conventional slices, Tiger runs at least one order of magnitude faster. Second, we run our Tiger over 200,000 recent apps. It is the largest study of this kind of work. Our research discovered a lot of new interesting types of token. This finding help us better understanding Android apps network traffic. Also, it highlighted that the code analysis-based approach is a promising way to fingerprint network traffic in Android applications. Here's my presentation. Thanks for all your listening. Thank you.
Hi, can you go back slides? Can you go back slides?
To which one?
To the experiment measurement. Go back. And back. Evaluation, yes, please. Okay. Have you considered? Okay, first of all, thanks for the work. And my name is Z. I'm from the Palo Alto Networks. You mentioned next generation firewall. Yeah, we're doing that. So we see a lot of traffic, definitely millions level. So I'm very interested about this work. It's very good work, and we appreciate that. And one question is like, have you considered when you do the print, have you considered the traffic generated by the SDK or library embedded into the app and differentiate with the traffic generated by the SDK with the native apps network communications when you do the imprint?
You mean the native code?
Yeah, for example, no, not native code. I mean, when you install an app, you definitely contain the app itself. I mean, the app developers communications between the app and its own server, and also the SDK talk to the advertisement servers, right?
Yeah.
So do you separate them and only consider that the communications between the app developer and the app developer server, or you also include the SDK's communication as well?
And do we consider the traffic from the server?
No, traffic generated by the embedded SDK, like advertisement SDK.
Sorry, I can't.
Okay, another question. So when you do the imprints, do you consider using the domain name because it's so simple?
Yeah, a domain name is one of tokens, but our imprint is not a single string. It's a combination of It's a combination of invariable tokens.
Right, right. Yeah. So when you compare the results, different apps using domain name that they talk to with using your imprints, what's the difference? Which one is better?
Oh.
Like if this app talk to Facebook.com, then probably this is a Facebook app.
Yeah. In our experience, we find that we can't only use a domain name because they are sometimes in a shared libraries, but we use a combination. So maybe one domain name appears in several apps, but while combining other tokens, so our imprint becomes unique to identify app.
If the domain name appear in different apps, most of the time it's SDK. You don't need that.
Yeah, in fact, we can remove the
That's
remove the
noise.
host, but in our this work we don't have to remove it because we have other tokens to construct imprint, and it can be unique to identify the app.
Okay, okay. Let's next slide.
Next slide.
Next please. Next please. So this is quite usual for developers to do that. So not very special case because app developers they are trying to identify the running environment. Also, sometimes they just maybe just a random hash put it over there as a default value. So we see that all the time. And
Yeah, we also see this situation. But
it's good observation. I mean, it's real. And can you go next? And the next. Yeah, I think those tokens, if you consider one suggestion is like if you consider combination and some of the statistic on those tokens and their token names, I mean entity names that they put into that URL, you
yeah,
might find that they can also be used for the imprint the traffic. Like the combination of them and the appears a sequence of it appears when they do the communication. Like when you first install the app, they will send an URL with certain pattern. Then later on they have another one. So the number of the different type of the tokens that appears in the URL is different. So
yeah.
it can also help you not only based on one URL, but you consider that sequence and their
Yeah.
types.
Yeah,
You can do the
we
imprint as
consider
well.
it. We get up every packet content, so not only including the URL, but a packet in a whole HTTP packet. So it
I mean a
containing
sequence of package.
or the sequence.
Yeah, sequence of the package.
But the the firewall can identify this kind of situation.
Yes, they have finance state machine.
Okay.
Okay, sorry.
Thank you.
Yeah, that's all.
Okay. Thanks for the great talk. Did you look at the fraction of imprints you found that are actually encrypted with HTTPS? Because the original motivation was to identify the imprints from the traffic. Did you look at that issue?
Sorry, could you say it again?
Okay. Did you look at the fraction of the imprints that are encrypted with HTTPS communication?
I'm so sorry. We can take it off now. Okay.
Let me say again. Did you look at the how many of the imprints were transferred over the HTTPS communication?
From the HTTPS communication.
Yeah.
Okay, we consider it. We know now many apps are use HTTPS, but it is surprise us in our data set. Just selected the mobile apps from Google Play, third markets, and PHS. They are all the up-to-date apps, but most of them still use HTTP. It surprised us too. Yeah, so we don't calculate detail ratio, but we have known that the most apps are still use the HTTP protocol.
Let me add one quick question. Do you have a plan to make this tool publicly available?
Sorry.
Do you have a plan to make this tool available to anyone? Can I use that tool?
This tool.
Yes.
Now we didn't public, but we can consider later. Thank you.
This is an interesting work, and I just have a quick question. So you kind of find out those tokens contained in the source files, and then later send to the network sync. Some question is, what if I obfuscate those tokens in the source files?
Okay.
Again, then I deobfuscate them at the runtime and then send out.
Yeah. First, in our data set, most applications are legitimate gaps. So the obfuscation is not very not a lot. But our approach is resilience for the obfuscation. It depends on the obfuscation's level. The because our work is combined static analysis and dynamic analysis. So if we find the network sink and we can extract the flow relation of the code, and if the obfuscation level is not too deep, we can still handle it.
So do you have like a dynamic analysis to run, right?
Yeah, we have. After we get a simplified slice, we modify the Android Delvic virtual machine to the PC platform, and we run each slice. We run each slice. Yeah, we run it.
Okay, thank you.
Thank you.
Yeah, last question. Hi, this is really great work. Thanks. I have a question. Like for many of the apps, they require logging, and I guess you can identify those cases, but you need a real credential to make it successful, right? How do you handle this case?
You mean the user login
Yes.
situations? In fact, we don't care about the trigger. We don't care about how to trigger the network activities because we go straight to find the network syncs, the packet sending APIs and the backward slice them. So we don't care how to trigger the activities. And so no matter how complex the trigger is, we can cover it.
From my experience, like when I run Android Monkey, like dynamic try to interaction with app,
Yeah.
I think I got like lots of errors when I invoke something I shouldn't invoke it without the credentials. So I guess I don't know how you can check those cases.
You mean how to use a UI exploration tool to to get through the user login
Yeah.
login
So
page?
when you get past the login phase, there's some actions require you to be logging, right?
Yeah, because yes, but our tool is not a pure dynamic tool. Our tool is a combination of dynamic tool and static tool. So we first we just find the we statically find the network APIs and do the static analysis on the code. So we don't care the triggers.
Okay, thank you.
Okay, thank you.